here we are again. It is the physics video lecture, Physics 203, video lecture 3. And we had gotten to the variational calculus last time. So I'll just briefly review. So last time we went from point mechanics, Newtonian point mechanics, to the variational principle. So I'll just write point mechanics, in which we have mass times acceleration is equal to force. In fact, we had it in the form external force, how did I write that? F sub I external plus F sub I constraining force. And just as with the internal forces that we had in the previous discussion, the constraining forces were able to be eliminated from the discussion, okay? So, but this time we pursued it and obtained the variational principle, and today we have to put some content there. And the variational principle is that this object here, kinetic minus potential energy, integrated over time, fixed boundaries, is equal to 0, and that's called the principle of least action. So the integral over t minus u is the action. And the variational calculus is so interesting and useful, and in this class we approach it in a number of different times. So for that reason, I'm just going to talk about the variational calculus independent of it being a kinetic and potential energy, just as a branch of mathematics, certain types of problems. And then we'll come back to the actual physics that we're going to pursue with it. So that was last time. This time, variational calculus. And I will start just with some problems. So historically, there was a problem in the old days when the smart guys sent each other problems in the mail, of finding the curve of least time. The idea was this: imagine 2 points A and B in the plane. B over there, it's fine. And you want to run a wire from here and have a bead slide down a wire with no friction in the least possible time. So the curve that would let a frictionless bead go from A to B in the least amount of time is what we're looking for. And so that's a problem that's formulated here in space, and the answer is an unknown function, a function that we don't know yet. So I'll just draw a little bead, frictionless curve, frictionless wire, and we want the least time. And so what we would need is an expression for the time, how long it takes to go down this thing given this curve y of x. And we can do that, and that'll bring us to a kind of a minimum problem, right? Least time, so we're trying to minimize something. So how do we do that? So frictionless wire, least time curve. That's well posed, I'd say. So what is the time if something's moving here? You know, as physicists, we could say infinitesimal time from distance equals rate times time. So we would have dl divided by v. So we would need a length element here and a time here along the y-axis. I'll call this y sub 0. So the length element, I'm just going to write it down for now because we'll spend time with different length elements. Well, actually, let's derive the length element here in the plane. So if we have some function y equals y of x, I'll just write y of x. And we have an x-axis and a y-axis, and we want a little length there. We can approximate it with dl squared equals dx squared plus dy squared. And this is the construction dl dx over dx squared plus dy over dx squared. And then, since we divided by dx, we're going to multiply by dx. Okay. So that is root 1 plus y prime squared dx. So that's our length element. So we have root 1 plus y prime squared dx. And now we have to find the speed. And the speed we would get with energy conservation. So we could say 1/2 mv squared plus mgy is equal to 1/2 mv0 squared plus mgy sub 0. Okay. And then we'll start at rest, and then we can cancel all the m's, and we get the familiar result v. Oops, here we go. We have the familiar result that v is equal to root 2g y0 minus y. Okay. Yeah. So we'll put that here, root 2g y0 minus y. And there's our infinitesimal time, and to get an expression for the time, we integrate both sides of this, and we'll have a well-posed problem. Go ahead and do that now here. So time t will therefore be this integral, and root 1 plus y prime, so it's y prime of x squared dx root 2g y0 minus y. Okay. Y is a function of x. Didn't have to actually write the argument in there. And we're going from x sub 1 to x sub 2, x sub a to x sub b. I'll just write x sub 1 to x sub 2. Fixed boundaries. And then you could bend that curve any which way. Maybe we could make the problem a little more plausible. The point is this. So you're going to have some curve that gives you the shortest time. If you were to take a curve like this red one here, you could make the time as long as you want. You just make this very gradual, and then after a long time it drops down into place. You could also have a curve that does something wild, like this lower curve, and that's clearly going to take longer. It's taking a longer route. So the idea is there's some optimization, and between these two type of extremes, you're going to locate an actual minimum that exists. Okay. So yeah, there we have the problem formulated, and how do we find the unknown function? The unknown function that will minimize this time. So find the unknown y of x that minimizes integral right here. Okay, that's pretty nice. An even simpler problem. So this is the one example. So the next example that we'll take all the way to the finish line, so to speak, is the shortest curve connecting, so the shortest curve connecting 2 points in the plane. And we know the answer to that, it's a straight line. So it's nice to have a problem whose answer you know, and then you can make all the steps transparent. So the shortest curve connecting 2 points in the plane, and we'll just say L will just be the integral of dl, which we already have here. So we're looking for 1 plus y prime squared dx from x1 to x2. So that's an easier problem than this one. This thing was a function of y and y prime. This is only a function of y prime. And what we're going to do is generalize this to problems. It says to of the form, we're trying to minimize phi, and that's an integral of f of an unknown function y, its derivative, and the variable there, dx, x1 to x2. I'll give you a problem later on that actually has the explicit x as well, and then we'll have the complete set of examples. So yeah, we want to generalize to a problem like this, in which the choice of y, or the y that we're looking for, minimizes phi. So phi is by y of x. Okay, so we're trying to find this unknown y of x in all three of these cases here. Now our straight line problem, or whose answer we know, this is the one that we can study the best, because I can draw a straight line in the plane and then show what we're going to do. So yeah, let's draw a line in the plane, x, y axis. These are the 2 points. There's x1, x2. We could label these 2 points A and B. There's the shortest curve. Now what we're going to do is imagine that we know the answer to all these problems. In this case, we really do know the answer. And we're going to choose a function that's very close to it. I'll use red. So if we have this curve's represented, so y equals y of x is the function we're looking for. So suppose we know the answer is the function that we seek. So this is the function. Then any function that is slightly different from this one, my red curve there is necessarily going to be longer. It's no longer the minimum. Okay. So I could construct functions then y tilde of x equals y of x plus epsilon g of x, and I'll show you what I mean by this. So epsilon g of x no longer minimizes the problem, okay? Because this is the one that minimized, and I'm adding something to it. It's the wrong curve now. It's a different curve. So y tilde of x minimizes phi, in this case minimizes L, when epsilon equals 0. So I'm constructing a function or a scenario where the minimum is found when epsilon is 0, and this thing here is the variation of the curve. And what we do is we stipulate that g of x, g of x1 equals g of x2 equals 0. So I take the function that I know and I add something to it that vanishes at the endpoints. Okay, because that way I can maintain the condition I'm going from endpoint to endpoint. Okay. So here let's assume that y equals y of x is the function that we're looking for, okay? Then this y tilde minimizes phi when epsilon is equal to 0, and now construct a function phi here, phi as a function of epsilon. Okay, this is just a great move, watch this. So we construct phi of epsilon is the integral f of y tilde prime x dx. I've now constructed a function phi of one variable that minimizes this thing here, x1 to x2, when epsilon is equal to 0, by construction, okay? And I'm going to use that as a necessary condition, because if we have a function of one variable that takes a minimum, takes on its minimum when epsilon equals 0, we can just use the first derivative criterion of ordinary calculus, okay? d phi d epsilon evaluated at epsilon equals 0 is going to be equal to 0. So that's our next statement. We've just constructed this thing. So we'll formulate that statement, and then we'll do calculation. So now construct so-and-so. You notice the g's are defined up here. So let me write d y tilde d epsilon is equal to g of x dy tilde prime d epsilon is equal to g prime of x, just from the definition of what y tilde is here. Okay, if I take the derivative of the g there. Okay, so now we have the situation d phi d epsilon evaluated at epsilon equals 0 is equal to 0. It's right here by construction. So let's go ahead and do that. So here's our expression here. Now d phi d epsilon is equal to, we're going to assume we can differentiate under the integral, exchange those limits, got x1 to x2, partial f with respect to y tilde of its arguments, and then dy tilde d epsilon, which is g, up there, g of x, plus partial f partial y tilde prime, and its chain rule, dy tilde prime d epsilon, which is g prime of x. There's a dx. This one we're going to keep in the same form, integral partial this one here we're going to integrate by parts. So what we end up with is df dy tilde prime times g evaluated x1 to x2 minus integral d dx df dy tilde prime g dx x1 to x2. Good, so make sure you note there, this was just a standard integration by parts. By the assumption right here, by g of x1 equals g of x2 equals 0, this boundary term vanishes by that assumption. So that's a 0. Then I can bring these integrands both under the same integral with a common g, and that will be integral partial f y tilde minus d dx partial f y tilde prime dx x1 to x2. Forgot to write the g here, didn't I? G dx. Now, in the limit, right, the evaluation of this at epsilon equals 0 just turns this expression to, just drops the tildes. Okay. Tildes go away. When epsilon is 0, y tilde is just equal to y. So I'm going to draw that conclusion. We find, we're almost done. We find that this integral here, if the tilde is gone, since we've taken the limit, so this integral prime, did I have primes over? Yeah. G dx is equal to 0. Fixed boundaries, x1 to x2. Okay, now what? This expression in the square brackets is in fact the differential equation that we're looking for. But we can't just declare victory yet because we're multiplying the square bracket by g. But because g is an arbitrary function, arbitrary except that it vanishes at the endpoints, because g is an arbitrary function, we can use what's called the fundamental lemma of the variational calculus and conclude that the expression in brackets itself is equal to 0. So I'm going to, I'll send this up here. Going to do that. That's the equation we're looking for. I'll sketch the proof of the fundamental lemma of the variational calculus, because that's a really standard type of technique. But so far we have, and I'm just switching the order in the expression, partial f partial y prime minus partial f partial y equals 0. That's the Euler-Lagrange equation. Euler-Lagrange. But the reason we can do this is because of the fundamental lemma of the variational calculus. So I'll just put a note here. Fundamental lemma of the variational calculus. And that is if integral f of x g of x dx from x1 to x2 is equal to 0 for arbitrary g of x, then f of x itself is also equal to 0. Then this capital F of x here is equal to 0. And you can see in my statement, this f of x is my square bracket. Okay, my g of x is the one I've been using there. So the proof is interesting. It's very simple. It's just by contradiction. Proof by contradiction, which is to say you just turn around this implication here. Proof, assume f of x is not identically equal to 0, then there exists an x0 element x1 to x2 for which, without any loss of generality, f of x0 is greater than 0. Okay, so what we're saying is that here I'll make my little sketch right here. Here's x1, here's x2, here's some point in that interval where f of x, capital F of x, is not equal to 0. Okay, so it takes on some little positive value there. By continuity, there is a little neighborhood around which the whole thing is still positive, okay, greater than some minimum number. So what we do now is we just construct g of x as shown in the picture. Right, I'm not going to formalize this. We construct a g of x that is 0, and then inside this little sub-interval, we just get a spike, goes back to 0. Right, that's one of those arbitrary functions that g of x is allowed to be, and the integral of this f of x, which is this, this little value here, times this spike, is clearly going to be greater than 0, not equal to 0. So now construct g is shown, then integral fg dx is greater than 0, and there's our contradiction when we assume that it is 0. Good. So this is a technique that's used many times in physics. You'll often see it essentially used when you're going from Maxwell equations. For instance, when you go from the integral to the differential form of the Maxwell equations, you make these types of arguments as well. So it's good to see a formal proof of it. This is a pretty formal proof. You could fill in the really formal stuff if that's your ambition. I think it's clear enough. So now we have our Euler-Lagrange equation. We haven't skipped any steps, and we want to do an example. And what we're going to do is prove that the shortest curve connecting 2 points in the plane is a straight line. And then I'll assign the other problems, which is a really interesting and fairly fun subject. Okay. So the example, I don't have it up there. No, we don't have it up there anymore. We're going to put down that straight line example for starters. And then we'll construct a few more problems, and we'll be on our way. Okay, the example was curve in the plane example. So the curve in the plane example was this one. Right? And we had L equals integral root 1 plus y prime. I'm not going to write that argument. It's 1 plus y prime squared dx. So in our formalism, here, f of y, y prime, and x is a pretty simple one. It's just root 1 plus y prime squared. So it is not explicitly a function of x or y, it's just a function of y prime. In the other examples we do, we'll have greater, more complicated cases. We'll have more complicated cases. We're going to start with this one because there's our equation, and you can see the df dy is 0. Okay, so it simplifies a lot. And now we have d over dx, df dy prime. Okay. But since that is now 0, we immediately have df dy prime is equal to a constant. Okay. So this is using the Euler-Lagrange equations. I actually should always write that thing down, have it in front of you. And I had it on the board. So that's a red star up there, and that's where I'm referring to. Okay. So df dy prime is constant, and there is f right here. So let's go have a look. If we differentiate that with respect to y prime, we have 1/2 root 1 plus y prime squared, and then inner derivative chain rule 2y prime equals constant. I can cancel these. I can get an expression like y prime squared is equal to c squared 1 plus y prime squared. Now I'm just going to solve for y prime. That's all I'm doing between these steps. So I have y prime is equal to, so y prime squared times 1 minus c squared. So I'm going to have c over c squared 1 minus c squared root. That's just a constant. I could give it another name. Okay. Oh, this is y prime. If I did that right, point is I can just solve for y prime and I find it's a constant. I'll call it capital C. And now, that's a differential equation that we can solve, right? Y of x is equal to cx plus d, another integration constant. And what is that but the equation of a straight line? Boom. So we proved our point. Proved our point with a nice example. And now we're going to do a couple more involved ones, and we'll set them up as homework problems. Good. Yeah, so the next thing to do, by the way, this is a second order differential equation. And so we reduced it to a first order differential equation just because since this was 0 and we had a first integral here, okay, so we reduced it to a first order differential equation. You can't always do that, and then you're kind of in trouble. So we're looking for cases where we can reduce it to a first order differential equation as well. There's another formula that'll come into play there to complete this whole system. But I'm going to start by formulating a couple more problems. By the way, the curve of least time is called the brachistochrone. I should write that down. And that's one of the problems that I'll put on this little list of problems. Now, I'm going to generate a couple more. And in fact, you know what I think I'll do? I'll formulate some problems, some homework problems now while I'm on the subject. So, homework. Find shortest curve connecting 2 points in space. And what we're going to have to do is extend the formalism to functions of many variables, which we will do before the hour is out. But I'm just going to put the homework formulation right now. So shortest curve connecting 2 points in space. And this is just Cartesian 3 space, so we know the answer there is going to be a straight line as well. That'll just be a slight generalization of that problem right there. So there's a problem, and then we're going to find the shortest curve connecting 2 points on the surface of a cylinder. Third one is find the curve that minimizes the surface of revolution, a curve that produces the minimal surface of revolution. And this one I'm going to generate right now, the problem. Surface of revolution. You know, so that we have a few to get started on. I just want to make sure those are in the notes. Okay, so let's talk about this surface of revolution. So for three, we have to first of all ask what's being described here. So suppose we have x, y, and z axis coming out of the board. And what we're going to do is find a curve here. How about another color? Find a curve that goes like that, and we're going to send this around the y-axis to produce this funnel structure. Maybe I can make it look symmetric while I'm at it. So we get this funnel structure here. Okay. And we want the surface area of this funnel, and then this curve here, y equals y of x, could be any number of things, right? Since you've got these 2 points that you're connecting, make them blue. You could do a straight line, you could do something that's convex, something that's concave, and so forth, concave, convex. You can do any number of them, but there's one that actually minimizes the surface area of this funnel. So that's what we're looking for. And this is a nice construction here, actually. So, right, we sent this curve y equals y of x around the y-axis. And now the area dA, we can say is equal to a little piece here that comes around. So we need the dA of that little ribbon. And we would have, it'll be 2 pi x times dl, which would be 2 pi x, and x refers to that point right there. 2 pi x, and then this root 1 plus y prime squared that we've already been using for dl. Okay. So here's our problem. We have an area integral 2 pi x root 1 plus y prime squared dx from x1 to x2. Okay. I'll just write here f of y, y prime, and x turns out to be this 2 pi x root 1 plus y prime squared. Now, do I have? Okay. So again, our Euler-Lagrange equation will allow us to solve this differential equation. So this is a function of x and y prime and not explicitly y, so we're in luck again. We are again in luck because the Euler-Lagrange equation can be integrated up pretty well. And if you don't recognize the integral, look it up. It's just a well-known function. Okay. So that's for problem 3. That's a minimum surface of revolution. Let's write out the Euler-Lagrange equation just so we have it right in front of us. D dx df dy prime minus partial f x equals 0. So once again, this derivative is actually equal to 0, so that this thing here is equal to 0, and we're solving the problem similar to how we did last time. Okay. It won't be quite as easy. The 2 pi you can take or leave, okay, just a constant. But we dodged a bullet, so to speak. This one will also be easy. Interesting problem. These two, I have to get to a multivariable case. So what we'll do is I'm going to go to the multivariable version of what we've just done, and it turns out we don't have to do much. We've done all the heavy lifting already, so to speak. We'll get the multivariable version of the variational calculus, and then we can tackle these other 2 problems as well. Okay, so what we're looking for now is not just a function, but a system of functions. So we'll call this thing phi again, and we're minimizing, for example, with the curve in space and the curve on the surface of a cylinder, those would be 2 variables, okay? But generally, we're going to have n type of functions here. So y sub 1 to y sub n, y sub 1 prime to y sub n prime, and x dx. So this is the form of our problem. Okay, so write that all out. And just for the record, y sub I equals y sub I of x, dy sub I, or y prime, just for the record, y prime dy sub I dx. So yeah, these are functions of x. Now we're going to construct, now let y sub I tilde of x equal y sub I of x plus epsilon g sub I. Epsilon sub I, g sub I of x. Okay, very important. There's the subscript g sub I of x 1 equals g sub I of x2 equals 0. So at those endpoints, these g's equal 0 again. It's always the same picture. You know, you get your point 1, point 2. This is your y sub I function, and then you're adding a little bit to it that vanishes at the endpoints. That's the idea. So what I've done now, I've done to every variable what I did to just one last time, but by construction, I now have a phi of epsilon 1 to epsilon n, f of y sub 1 tilde to y sub n tilde, y sub 1 tilde prime, y sub n tilde prime, x dx, x1 to x2. And here's the thing, by construction, because we're using the same arguments we did last time, we're minimizing something. By construction, this phi has its minimum when this total epsilon, all components of epsilon, think of it as a vector, when they all vanish, okay? But the construction is very important, that what we're doing by having a g sub I, epsilon sub I, we're varying this thing one variable at a time. So y sub 1, y sub 1 prime, okay? Y sub 2, y sub 2 prime. What this means is, by construction, phi has a minimum when epsilon equals 0. This means that d phi d epsilon sub I evaluated at epsilon equals 0 is equal to 0 for I equals 1 to n, and that just gives us that calculation we already did n times. They're all exactly the same. So we've done it already. We've done the calculation. We're going to get n Euler-Lagrange equations out. So we're going to get the same thing. So what we end up with is d dx partial f partial y sub I minus partial f partial y sub I prime, y sub I equals 0, I equals 1 to n. So that's fantastic, right? Really important point that is built in here is that it's utterly necessary, it's required that these variables all be independent of each other. Okay. You have y sub 1 to y sub n, y sub 1 can't be a function of y sub 3 or something. These variables have to be independent. And otherwise this construction doesn't work, right? Because we're independently varying each one of these partial with respect to epsilon sub I, which picks off y sub I, has to vanish. So they all have to vanish at the same time, independently of each other. Then we get this form n times. And we're not specifying any type of coordinate at this point, right? It's very general. So the note I want to put here is note the y sub I functions must be, or variables must be, independent of each other. Independent. And later on we'll come up to a case when they're not, and if they're not independent, you can have some very beautiful looking equations and they're wrong. They're completely wrong. So I'm gonna I'll stress that when the time comes. Okay. Independent variables. Okay, we have our Euler-Lagrange equations, and since we have this for this full set, there's one more major equation we need, and then we'll have the formalism in hand. Let's see how we're doing for time here. Oh man, time flies. Okay, still have a bit to do. What I'll do is talk about these problems here, because we can't set up the length elements now. So we talked about problem 3, problems 1 and 2 I'll set up as well. Okay, got this. So the question is now, what are the length elements for problems 1 and 2? Because we're talking about the shortest curves, and we could even extend it to the shortest curve on a sphere. I'm almost tempted to do that one. So just to have that in front of us here. Length elements, note on length elements. So we have dl is equal to v dt as physicists. So even though we're just doing geometry here, as physicists, we know that. And so if you have a set of coordinates where you can find the velocity in terms of a parameter, then that's how you can get your dl. Okay. So for Cartesian coordinates with more than one variable, you could have dl equals root 1 plus y1 prime squared plus y2 prime squared. If you have two axes and you want to have the third axis, we're talking about space, so we have y1, y2, y3 if we want. So we can do something along those lines, and what you call this letter is up to you. Okay? So we can do that kind of thing. What about, so this is Cartesian, what about on the surface of a cylinder? Cylinder, question mark. Well, then you need the length element in cylindrical coordinates. So the choice of the proper coordinates is very important. That's one of the themes of the entire semester. So what is the length element in cylindrical coordinates? And once you have that, you can, you're on your way. Question mark. So for these problems, this is one version of a length element in Cartesian coordinates, because we've just added one to the one we already had, 1 plus y1 squared. We have another. And in cylindrical coordinates, I'm going to let you guys figure that one out. You look up cylindrical coordinates, how do you get a length element? Basically, you've got cylindrical coordinates and the radius is constant. The rho is constant. So you've got a z and a phi variable. But yeah, once you have that, and then sphere, if we have the same problem on a sphere, so 2 points on the surface of a sphere, then we would need the length element in spherical polar coordinates. Spherical polar coordinates. I'm holding off whether I assign that one. It's a classic problem as well. The cylinder problem is kind of easy, interesting, because you're wondering, okay, we form a cylinder out of paper. Here's a cylinder. And then we've got 2 points on the outside of this, and we connect them with a line. So I'm going to ask you to of course, do it formally with Euler-Lagrange, but the idea is this. You could have actually drawn a straight line on this paper, and then that's certainly the shortest distance between 2 points on that surface, and just because you've wrapped it up into a cylinder doesn't change that. It's still the shortest distance, right? And therefore, the answer is actually it's a helix. Right? It's a part of a helix, but what you're going to do is prove it using the Euler-Lagrange formalism, which won't be difficult. So we have this shortest curve, this surface. The minimal surface one I already set up. We have the formalism for many variables. There's one more formula we need, like I said, to be complete with this. And so that's what I'm going to generate now. So what we are going to be working with is we have this kind of scenario. We have this function f. We have variational calculus. Gives us differential equations that allow us to determine these unknown functions. So we have this function f, and we have the Euler-Lagrange equations. Now I'm going to erase this and derive what's called Euler's second form. And I'm just doing the simple version of Euler's second form, but we'll just call it Euler's second form. It's the incomplete version, the one we need. So let's title this Euler's second form. Euler's second form. So I'm just going to write it down, and it looks like this. And I'll call this a theorem. If this function f up there, I just erased, if f is not explicitly a function of x, okay. So I'm going to use this nomenclature often enough. So f equals f of y1 to yn, y1 prime to yn prime, but not the x. So it's just a function of these variables. If that's the case, then this expression here, the sum partial f y sub I prime, y sub I prime minus f, so f is outside the summation, is equal to a constant. And what this does is it potentially turns your problem into a first order problem, because this is now a first order differential equation. So it helps you out. And the proof, I'm just going to, you can squeeze it in here. The proof is I'm just going to differentiate this whole thing with respect to x. So d dx of everything here is equal to sum over I. I have a d dx partial f partial y sub I prime times y sub I prime, and still under the sum I have a partial f y sub I prime. Now I'm differentiating the y sub I, so I have a double prime. Now this function has all these variables, so when I do the derivative with respect to x, I have a chain rule, so I'm going to have df d y sub I, y sub I prime, chain rule, and then I'll do another summation for the second set there, minus df dy sub I prime, y sub I double prime. Okay. So now I've taken all of those derivatives, and I can see that here, this was under one. I can see that this df dy sub I prime, y double prime, and this one cancel. Okay. And so we're left with these two. But these are going to have a common y sub I prime, so we're going to get the following: sum over d dx partial f y sub I prime minus this partial f y sub I square bracket y sub I prime. So that's what this complete derivative with respect to x gives us. And what you'll see is what's inside the square bracket is just the Euler-Lagrange equation. So each one of these individually vanishes, and therefore this whole thing vanishes, and that proves it. So this is an important expression. The case where f is not explicitly a function of x gives us this constant here. You know, a little downstream when we're doing Lagrangian mechanics, this is going to be a conservation law. Right now it's just the first integral, help you solve the problem. Okay, so now we have all of the ingredients. That'll work. I think I'll put one more good problem up here. to add to this list of homework problems. Got one more really nice one. Two problems while I'm on the subject. How about another? So this last one, okay, we have these lengths, we have that stuff. Okay, the catenary. This one is going to bridge the geometry and physics situation. So what is the catenary? The catenary is the curve adopted by a chain or rope just hanging under its own weight in gravity. So that's the catenary. So there's up and G is down. Okay. So what is the function of the catenary? Now it turns out that you can get that function using the variational principle, but I don't really have any proof that the principle is true, namely that this curve minimizes the potential energy. Minimizes the potential energy of this hanging chain here. So we're going to prove, let's say we'll formulate this as a variational problem, and the other proof will come later. So the catenary minimizes the potential energy of a hanging chain catenary minimizes potential energy of a hanging chain. That's why it has this beautiful shape, like a bridge, a necklace, that kind of thing. Okay, it's really a hanging chain. So the potential energy du we can say is dm times g times y, right? dm times g times y, and then we'd integrate that up. This dm would be a linear mass density times dl times g times y. So linear mass density, so constant linear mass density and because of that, g is a constant, lambda is a constant, and then we can have y dl, which is root 1 plus y prime squared dx. So there's our integral. Potential energy equal to, I'm going to pull the g and lambda out. That's actually an interesting point to be made. So g and lambda are just constants, uniform mass density, gravitational acceleration. And under the integral we have y root 1 plus y prime squared dx, x1 to x2. So here's our potential energy, and we're looking for the curve, the function y of x, that would give us the minimum of this. There's actually some physics in here, assuming that this principle is true. What we're claiming is the shape doesn't depend upon the magnitude of the gravitational field. It doesn't depend upon the linear density of the rope, of the chain. Okay, but here we have f equals f of y and y prime, and not explicit x. Okay, I'll just write y. Actually, I won't write anything. You guys know what we're talking about. It's y and y prime and not f of x. So this is an example where we can use that theorem that we just wrote down. It's only going to have one term in this sum here, df dy prime times y prime, and then minus f. So let's add that to the mix, and we have some really nice variational problems going on for the homework. And then we can already make our way back to physics. Anything else here? Well, no, you know what? To just complete this whole exercise, I will do the catenary with Newton's law, and then we can also integrate that up. That'll have a really nice complete treatment of what we're trying to do. So I've stated this catenary minimizes potential energy of a hanging chain. The proof of that will be if I derive the function of the hanging chain using Newton's law, right? Newton has authority in these matters. And then if that answer corresponds to the answer we get out of this, then we could say, oh, that principle is true. Okay. That's going to be our logic. So I'll do the catenary with Newton's law, and then we'll have a nice complete treatment here. In the variational calculus. Okay, so catenary once again. Catenary Newtonian style. Okay. This is really a nice calculation. Just a moment. Okay, back to discuss the catenary. We'll wrap this up. Okay, so let's draw this catenary again. That's basically what they look like. We're going to put it in a coordinate system, and the coordinate system I'll just put over here, x and y, up and down is the y-axis. So here's what we do. The first thing, we just go to the minimum point on the catenary. We can just get rid of the left half, and then this thing will be supported by a tension. Okay. And then we can go up to some arbitrarily point here in the x direction, xy, and cut this away, and then we will have a force. Okay, so we've got a tension here and a force there. We'll also see that there's an angle with the horizontal being made, and we're just going to use Newton's law, net force equals 0, because we're in equilibrium. So now we have minus tension plus F cos theta equals 0. Okay, in the x direction, and in the y direction, we've got minus mg, the weight of this thing is, right, pointing down, plus f sine theta is equal to 0. So we're going to eliminate this force F, and then what do we get? Sine theta over cosine theta is tangent of theta, and then we have mg over t, the tension. Now you got to convince yourself that the tension is constant. This tangent of theta, however, is the derivative dy dx of that unknown y equals y of x function that we're looking for. The g and the tension are constant, we'll pull them out. The mass is that lambda dl. So lambda is the mass is the integral of the lambda dl. So it's lambda integral root 1 plus y prime squared dx. Okay. And because x has been unspecified here, we're going from 0 to x, and this is an integration variable. So this is our problem according to Newton's law. And let's just make this a little nicer. This g lambda over t is just one constant. We can just give it any name we want. It's a constant, it's outside of the thing. There's our unknown function. So this is also the homework problem. And let me give you some hints. Hint. The first one is differentiate both sides. In the fundamental theorem of calculus, you get d squared y dx squared. You get the integrand evaluated at the upper boundary. Okay. So differentiate d dx of the whole thing. The second hint is to let z equal y prime, and then you'll have a first order differential equation, comma, then integrate. Okay, so that's also the homework problem, and that makes a nice complete set. You can do these in any order you want. Once again, take the derivative here, get d squared y dx squared, you end up with the integrand evaluated at x. And so you've got second derivative, but you got a first derivative here. That's why this substitution allows you to go back to a first order differential equation. Okay, that's enough for now. Next time, we'll actually take it from here back into physics and start up with Lagrangian mechanics. We'll talk a bit more about this stuff, but then we're into Lagrangian mechanics. Okay, good. See you next time.